Okay, let us start our session. Good morning, everyone. I am Danya Jose, guest lecturer from the Department of Physics, St. Xavier's College for Women, Alva. I heartily welcome you all to the session on the light matter interaction, a quantum revelation organized by the Postgraduate Department of Physics and Research Center, St. Xavier's College for Women, Alva. Kindly cooperate with us and follow the guidelines for the proper conduction of the webinar. During the session, keep your audio muted and video switched off. Don't present your screen during the webinar session to avoid unnecessary disturbances. Kindly write your name and address in the chat box after the recording gets started. This would be an hour-long talk followed by an interactive session. Participants can post their queries in the chat box, which will be discussed at the end of the presentation. Towards the end of the webinar, the feedback form will be shared in the chat box, which should be filled by the participants to get your e-certificate. Now, I invite Dr. Sheena Xavier, Head of the Department of Physics, St. Xavier's College for Women, Alva, for the welcome speech.
Thank you, Danya. Good morning to all. Respected resource person, Dr. Pius Augustine, Assistant Professor of Physics, Sacred Heart College, Thevara, dear colleagues and my dear students. National Science Day is celebrated in India on 28th February each year to mark the discovery of Raman effect by Indian physicist Sir C.V. Raman. Today, as we celebrate the National Science Day, it is customary that we go into the relevance of science in the present day context. When the pandemic breakdown came into effect globally, science and its implications took over as a platform to reach every corner of Earth. Scientific research brought in effective mechanisms as vaccines to contain this global pandemic. Today we have with us Dr. Pius Augustine to give an insight into the relevance of this day and its objective to growing up generation. He started his career as a higher secondary school teacher from 2005 onwards and joined Sacred Heart College in the year 2016. He took his PhD from Indian Institute of Technology, Madras in the year 2017. He has published several research papers in reputed journals and bagged Best Poster Awards in international and national conferences. He is reviewer of 3 Elsevier journals. Recently, he has received the Research Award, Teacher Associateship for Research Excellence from DST, to carry out research at Indian Institute of Science, Bangalore for 3 years, starting from December 2020 onwards. On behalf of Department of Physics, St. Xavier's College for Women, Alva, and all present here, I extend to you, sir, our most cordial welcome. I would like to appreciate and thank the Academy of Physics Teachers, that is APT, and DBT Star College Scheme for providing financial support to the department to celebrate the National Science Day. I also take this opportunity to congratulate the coordinator, Ms. Danya Jose, Dr. Vimala George, and all the faculty members of the department for planning and organizing the programs of this National Science Day. Hearty welcome to all. I cordially welcome all my dear students and wish you all a fruitful and interactive session with the esteemed resource person. Thank you and may God bless you all.
Thank you, Sheena ma'am. Now let us start our session and I will invite our speaker, Dr. Pius Augustine Sir, Assistant Professor, Department of Physics, Sacred Heart College, Thevara. Sir.
This is a 1964 photograph by Doc Eggerton. A bullet piercing an apple in a millionth of a second. This could be taken with a camera which takes frames so fast, a millionth of a second. That is, this camera must be taking 1 million frames of the bullet motion in 1 second. If we slow down the video 1 millionth, then we will get one frame which is shown here. Science and research are so advanced, and now there are cameras which can take frames even 1 billion or 1 trillion, or even femtophotography which can take 10 to the power 15 frames in 1 second is possible. With this amazing femtophotography, even slow motion videos of light in motion can be created.
Suppose you turn a laser pointer
Sibrana.
on and off so fast, then you will be sending a laser shot. If this on and off happen in 1 trillionth of a second or a few femtoseconds, then the laser source will release a packet of photon approximately a millimeter wide, which advances as a laser bullet with velocity 3 into 10 to the power 8 meters per second. What's the velocity of bullet from a gun? Maybe 500 or 1000 meters per second. So that is, light bullet is about 1 million times faster than an ordinary bullet from a gun. So in this photograph, the light bullet is allowed to pass through a bottle, a Coca-Cola bottle, and it is photographed using a femtophotography and viewed in slow motion. Light bullet needs just a nanosecond to cross a Coca-Cola bottle, which is about 15 centimeters long. So we will see that quickly.
Good morning. Greetings of the day. It's a pleasure interacting with vibrant Saviorites of the physics department. Thank you very much for the warm introduction. I extend my thanks to the organizers of the National Science Day celebrations, the head of the physics department, Dr. Sheena Xavier, Dr. Vimala Josh, Ms. Dhanya ma'am, other faculties and students for giving me an opportunity to speak on this beautiful day. I am also the coordinator of Physics Association at the Sacred Heart College. We call it SPARK, as such Physics Association for Recreation and Kaiser. We do have got a few activities these days. So on behalf of SPARK as well, I extend all good wishes of the day to all dear students. Also, I like to mention that it's a blessing to be a science student, a young scientist, and develop a scientific temper and scientific attitude in our day-to-day activities and interactions. February 28th is celebrated as National Science Day in India to mark the discovery of the Raman effect by Sir C.V. Raman on February 28, 1928. Sir C.V. Raman received Nobel Prize in Physics in 1930. In India, we have got a scientific council, National Council for Science and Technology Communication, NCSTC, a program of the Government of India for the popularization of science, dissemination of scientific knowledge, and inculcation of scientific temper. In 1986, this National Commission proposed to the Government of India to designate February 28 as National Science Day, and the first National Science Day was celebrated on February 28, 1987. So National Science Day celebrations are a motivational call for every budding scientist of our country to think differently, think vibrantly, or think scientifically. Of course, an invitation to bring laurels to the country again. This year, 2021, theme for National Science Day is Future of STI, Impacts on Education, Skills and Work. I do not elaborate this theme, but science, technology and innovation. It is really an appropriate and fitting theme in the present scenario. People across the globe realize the significance of scientific research to make our life beautiful on this planet as we pass through an year of lockdown, quarantine, isolation, etc. We face these things. Science is a body of acquired and reliable knowledge, acquired in a systematic manner. Religious books speak, God is knowledge. Let there be science. Let people acquire knowledge. Let them celebrate Diwali. Tamasoma Jyotirgamaya. So today I speak on light, light matter interaction, a quantum revelation. So here we will try to refresh our acquired knowledge to celebrate light matter interaction. This is 12th grade physics. Start with static electricity. Around a stationary charge, there is stationary electric field. A modified space, that is then Coulomb's law. Then comes electric current. Charge in motion is described. As the charge moves, distance to a point in space is changing. Then we say the electric field varies and it defines magnetic field. A current carrying wire is a source of magnetic field. Then electromagnetic induction and alternating current. A combination of all these describe electromagnetism, which accounts classical picture of light. So basically, light is a form of energy which produces sensation of sight. In 1690, Newton proposed corpuscular theory of light, which was accepted for over 100 years. But Newton's theory failed to explain various phenomena exhibited by light, like interference, diffraction, etc. So, in order to explain these phenomena, Huygens proposed the wave theory of light. He believed that light was a longitudinal wave, and that this wave was propagated through a material medium he called ether. Propagation of a wave through a material medium depends on elasticity of the medium. Since light can pass through vacuum and travels very fast, Huygens had to propose some rather strange properties for the ether. For example, it must fill all space and be weightless and invisible. For this reason, scientists were skeptical of his theory. Later, Michelson-Morley experiment confirmed the absence of ether. Then came the most brilliant mind of the period, James Clerk Maxwell. In the latter half of 19th century, he proved that light is electromagnetic wave, which does not need a material medium for propagation. Maxwell is considered as one of the men who changed the world and is treated as the most profound scientist between Newton and Einstein. This Maxwell's electromagnetic theory was a classical theory which brought together electricity and magnetism first time, and light as different manifestations of the same phenomenon. Maxwell's equations for magnetism have been called the second great unification in physics after Newton's work. The electromagnetic radiation is one of the many ways that energy travels through space. The electromagnetic spectrum or radiation is classified based on the way they interact with matter, which in turn depends on the energy of the wave, or say frequency or wavelength of the wave. So, you know, higher wavelength side is radio waves, which is having lower energy or frequency, and the other extremity is gamma radiations, which are very short wavelength radiations. Then heat from burning fire, light from the sun, X-rays used by doctors, or energy we used for cooking the food in microwave. All these are different kinds of electromagnetic radiation. So all these waves can propagate through space as electric and magnetic field variations, which are perpendicular to each other. While these forms of energy might seem quite different from one another, they are actually related, or in that they all exhibit wave-like properties, electromagnetic waves. So by the end of 19th century, the battle over the nature of light, whether it is a wave or a collection of particles, was seemed over. Maxwell's electromagnetism took its place as a foundational element of physics, along with Newtonian mechanics and thermodynamics. Great. So after a long time battle, it was like the problems regarding the nature of light was almost settled. Then came the revolutionary physics in the beginning of 20th century. A new interpretation for emission of light by heated objects brought in a new physics for atomic world. That is a radical departure from the classical theories of Newton and Maxwell. The birth of quantum mechanics. Again, the question of light and interaction of light with matter was reopened. So this picture, this is a very beautiful photograph showing the architects of modern physics. In our physics department in research college, we have this photograph on the wall, a very big photograph. Nice. A big salute. So here it is black body radiation spectrum. It is the spectrum of light emitted by heated objects. Heated objects can be heating element of a toaster, a filament of a light bulb, sun, etc. It has been found that spectral intensity of the black body radiation peaks at a particular frequency, which increases with temperature of the hot body, which emits the radiation. For example, a body at room temperature, say 300 Kelvin or so, will emit radiation with peak intensity in the far infrared radiation, far IR range. A toaster filament, which is at a temperature of about 700 Kelvin, or say a filament of a light bulb, which is approximately 2000 Kelvin, they will show peak in the infrared region. That is, as the temperature of the hot body increases, the peak frequency seen in the spectrum shows a shift towards visible range. Sun, which is at a temperature of 6000 Kelvin, is a black body. Sun emits radiation which peaks in the center of visible range. So in 1890, scientists found that the calculations of the spectrum of black body radiation based on classical electromagnetic theory and thermodynamics could not duplicate the results of careful measurements. In fact, the calculation predicted the absurd result. That is, at any temperature, the spectral intensity increases without limit as a function of frequency. In 1900, German physicist Max Planck could succeed in calculating the blackbody spectrum. He could match the experimental results by proposing a revolutionary idea, that is, elementary oscillators at the surface of any object will emit and absorb electromagnetic radiation only in discrete packets. And the energy of the packet will be proportional to the frequency of the radiation. That is, E is equal to h nu. And the constant of proportionality, what we call Planck's constant, was determined by comparing the theoretical result with experimental data. And the value is 6.626 into 10 to the power minus 34 joule-second. Actually, Planck did not offer a physical basis for the proposal. It was largely a mathematical construct needed to match the calculated blackbody spectrum to the observed spectrum. It was Albert Einstein in 1905 gave a groundbreaking physical interpretation to Planck's mathematics. He proposed that electromagnetic radiation is itself granular or emitted as photons called quanta with energy h nu. He applied thermodynamics arguments on radiation field, which obeyed Planck's radiation law and established quantum nature of light. He used his quantum theory to explain the phenomenon of photoelectric effect, which could not be explained using wave theory of light. That is, light of suitable wavelength, when impinged on certain materials, electrons or electricity will be produced. And Einstein got Nobel Prize in physics. And Einstein proposed quantum theory of light, which presented light as packets of energy, that is light photons, and E is equal to h nu, where nu is the property of wave, that is frequency, and h nu is the energy packet, that is property associated with photon or particulate. That is a beautiful relation, equation connecting wave-particle duality of light. And Einstein applied a very simple but profound physics, that is energy conservation, to explain photoelectric effect. It is shown half mv square is equal to h nu minus h nu square. We are all familiar with that. So in the figure, 3 different lights impinge on potassium, which is having work function 2 eV. So only light having energy more than 2 eV can cause ejection of electron. So when blue light of high energy falls on, the emitted electrons are having higher kinetic energy. It's a beautiful example of light-matter interaction due to quantum nature of light, a new world of science. Also, Einstein's explanation on quantum theory of light led to the discovery of another light-matter interaction, the most profound scientific discovery of the 20th century: laser, light amplification by stimulated emission of radiation. Here is Compton scattering, another evidence. In 1922, American physicist Arthur Compton received Nobel Prize for his study on scattering of X-rays from electrons. He analyzed the process as collision or interaction between X-ray photons with electrons. Conservation of energy and momentum principles were applied to explain the interaction. And he incorporated the relation between momentum and energy for a classical electromagnetic wave to an individual photon, say P is equal to E by C, h nu by C, or h by lambda. And he could derive an expression for the wavelength shift of scattered X-rays as a function of their scattering angle. That is what is given. And this Compton effect can be considered as another convincing evidence for the existence of particles of electromagnetic radiation. Now the question, where does light come from? Classical electromagnetic theory predicted light as electromagnetic wave, and accelerated electric charge is the source of electromagnetic wave. Here 2 atom models are depicted. First one is Rutherford's classical model of atom, and then Bohr's quantum atom model. So Rutherford, through his alpha particle experiments, established the presence of a concentrated positive massive region we call nucleus. However, the electrostatic interaction between positive nucleus and this negative electron makes electrons accelerated charge inside the atom. So as per classical electromagnetic theory, accelerated charge would release energy, and hence electrons would spiral inward and finally blast into the nucleus, which questions the stability of the atom. For stability of atom could not be accounted with the Rutherford atom model. So to settle the issue, Bohr proposed the first quantum model of atom. He presented a few postulates. Electrons revolve around the nucleus only in stationary orbit. When they are in stationary orbit, electrons will not radiate energy. Why it will not radiate energy? It is like that only. It will not radiate energy. He postulated. It was experimentally and theoretically verified at later stage. So Bohr calculated the quantized energy of electron in the orbit of an atom, and he got the expression En is equal to minus mz square e raised to 4 by 8 epsilon 0 square n square h square, where n is the principal quantum number which is the denominator. So it's a negative energy. That's an attractive energy. So outer orbits will have higher energy, and electrons in the inner orbits will have lesser energy. He predicted that electrons will radiate on energy only when it moves from higher orbit to lower orbit. The difference in energy will be radiated as light quanta hν. So here atom is the basic unit of matter, or we can say the internal structure of matter exhibits quantum nature. So light is having quantum nature, internal structure of matter or atom is also quantized. So quantum light can interact with matter which is also having quantized internal structure, and there will be associated energy or modulations in energy which can be widely explored, and that became a powerful experimental tool in material research, what we call spectroscopy. So spectroscopy is developed as a result of cumulative work by many scientists over many decades. Generally, Sir Isaac Newton is credited with discovery of spectroscopy. What is spectroscopy? It is nothing but a light-matter interaction and response. So there are various kinds of spectra. We have seen absorption spectra, emission spectra, etc. So basically, the absorption and emission of light do not take place as continuum, but as packets of energy called photons. So any region of electromagnetic spectrum or frequency of the light, there will be light photons, E is equal to h nu, which can interact with matter. So when a continuum of light, that is a broad range of wavelength, is allowed to fall on a material, particular light photons which have energy or frequency match with quantum differences in the intrinsic energy of the material. Energy or frequency which match with the quantum differences in the intrinsic energy of the material only will be absorbed by the material. So the spectrum of the light after the interaction with matter will have some missing frequency which was absorbed by the material, and we call it absorption spectra of the material. Similarly, the emission spectra. So we have seen hydrogen atom spectrum that is Lyman series, Balmer series, Paschen series, etc. So both absorption and the emission spectra are characteristics of the material which absorb or emit the radiation. And the analysis of the spectrum, what we call spectroscopy, it will speak about the nature of the material which absorb or emit the spectrum, and in turn characterize the material system or material chemistry. And this characterization technique is what we call spectroscopy. So spectroscopy is nothing but an analysis of the interaction of quantum light with quantized energy within the material, which reveals the nature of the material. So we have an unknown material. Suppose we have an unknown material or a new material. Then spectroscopy will reveal the nature of the material, a quantum revelation of something which is unknown. Basically, spectroscopy is an experimental science which reveals most of the developments of quantum mechanics, its theories, predictions, etc. Or to say, spectroscopy is an experimental verifications of the predictions of quantum mechanics. In chemistry, spectroscopy helps to identify and analyze molecules and the new molecular compounds. So by definition, matter is anything which occupies space and will be in atomic or molecular forms, and atoms and molecules of matter are associated with various kinds of energy. For example, atomic excitation and de-excitation, there is energy involved. Molecular rotation, molecular vibration, then energy of electron, maybe energy due to orbital motion of electron, or energy due to spin motion of electron, or nuclear energy, or nuclear spin energy, translation motion. So many kinds of energy will be associated with material or matter. And quantum mechanical studies have established that these various kinds of energies associated with material systems are quantized. That is, rotational energy is quantized, vibrational energy is quantized, spin energy is quantized, nuclear energy is quantized, etc. That is, all these various energies of the material systems will not be continuous, but a definite, discrete quantum of energy. These different quantized energies of a particular material system will have precise values, which are characteristics of the material system. So when electromagnetic radiation of appropriate energy interact with material system, one of these quantized energy may go to the next discrete state, or may come down to lower discrete quantized energy state, and accordingly a particular light quanta will be absorbed or emitted in the interaction, which can be analyzed and the material may be identified. So the quantum interaction of light and matter gives a revelation about the nature of the material. For example, radio waves while interacting with molecules, there will be vibration in the spin of electrons or nucleus. And the precise variation may be detected with advanced instruments, and the spectroscopy is known as nuclear magnetic spectroscopy or magnetic resonance spectroscopy, or electron spin resonance spectroscopy. So these are different spectroscopy which we study in MSc class. So again, microwave radiation when interact with matter, it modulates the rotational energy of polar molecules. That is, there will be change in the dipole moment of the molecules due to rotation, which will be picked and analyzed. Similarly, infrared spectroscopy, in which variation in vibration energy of the molecules will be explored. Then we have visible and the UV range of electromagnetic spectrum, and the spectroscopy is known as UV visible spectroscopy. Then X-ray photoelectron spectroscopy. Auger electron spectroscopy. So various spectroscopies we come across in research field. So today we celebrate National Science Day to commemorate Raman effect. During the period 1928 to 1930, the research community had identified a profound scope in developing Raman's research result as a spectroscopic tool to figure out the intrinsic nature of material systems, say molecules in solids, liquids, or even gaseous systems. So we call, today we call it Raman spectroscopy. So this is a scientific background. I'll just give a little, that there is a lot of stories behind Raman, how he came across this in his discovery and all those things, so that you, today my students also release one National Science Day talk. They have given a beautiful description of Raman and his that is historical background of his spectroscopy. So here I am just trying to give you some scientific background what Raman effect is. So Raman effect is a phenomenon in which there is change in the wavelength of light that arises when light beam is deflected by molecules. When a beam of light traverses a dust-free transparent medium or sample of chemical compound, a small fraction of the light emerges in direction other than that of incident light beams. Most of this scattered light is of unchanged wavelength or frequency. A small part of the scattered light will have different frequency or frequency different from that of the incident light, maybe higher frequency or lower frequency compared to the incident radiation. So when light interact with matter, solids, liquids, or gas, the light photons undergo collisions with molecules. There are two possibilities. One is elastic collision and the other is inelastic collision. So if it is elastic collision, there is no transfer of energy from photon to the molecule or from molecule to the photon. And the photon will be scattered without any change in energy. And the scattered photons will have same energy as that of incident photon, and we call it Rayleigh scattering. There are certain equations for Rayleigh scattering. While analyzing scattered Raman spectrum, there will be an unmodified line, which is nothing but Rayleigh reflection. And additional, there will be spectral lines correspond to higher frequency and lower frequency. They are called anti-Stokes line and Stokes lines, and can be accounted with the quantized energy interaction between light and matter. Suppose the incident photon of energy h nu collide with a molecule having kinetic energy half mv square and intrinsic energy say E1. Intrinsic energy we can take in, it is written E. So when it is interacting, then by applying conservation of energy, we can write the combined energy before interaction is equal to combined energy after interaction. That is h nu plus half mv square plus E, which is before interaction, is equal to, again, energy conserved, h nu 1 plus half mv1 square plus E1. Subscript 1 indicates final data after interaction. And there is no change in temperature during collision, very instantaneous process. And so the kinetic energy on either side is same. So we can easily remove kinetic energy terms, and the expression will be h nu is equal to h nu 1 plus E1 minus C, or h nu 1 plus delta E, or nu 1 is equal to nu minus delta E by h. So this equation, again, there are two possibilities. We call Stokes lines and anti-Stokes lines. If the molecule gains energy from the incident photon and goes to a higher energy level E1, then E1 minus E is positive, or delta E is positive. Then the energy or frequency of the scattered radiation will be decreased, or nu 1 will be less than nu, because nu 1 is equal to nu minus delta E by h, or nu minus delta nu. So the frequency of the scattered photon is less than that of the incident photon. Then the modified Stokes lines will be on lower frequency or longer wavelength side of Raman spectrum. Just reverse will be the case in anti-Stokes lines. In anti-Stokes lines, scattered photons will have higher frequency of higher energy. Where does this additional energy come from? That is, actually some of the molecules may be originally in excited state. So it may lose some energy to the photon during interaction, and molecules will go from initial higher energy level, maybe E, to a lower energy level E1. E1 will be less. Then E1 minus E will be negative, and nu2 will be nu plus delta. So frequency of the scattered photon is higher than that of incident photon. Or anti-Stokes lines are on higher frequency or shorter wavelength side of the Raman spectrum. A precise analysis of the magnitudes of these differences in energy that will give, or it could be due to variation in the quantized rotational energy or vibrational energy of atoms and molecules. So Raman effect is another light matter interaction due to quantum nature of light, which can reveal material characteristics. So far, so I was trying to share a series of light matter interaction and related quantum revelation. Now, before we wind up, I'll touch upon a little bit of my current research at the Indian Institute of Science, Bangalore. So here we are working on a photo detection, which is also a light matter interaction. So photo detectors are optoelectronic devices that convert the optical signal into an equivalent amount of detectable electrical signal through light matter interaction. So in Bohr atom model, we have seen that for a particular atom, there is precise energy levels. But when atoms come close to form, or closer and closer to form solids or materials, there will be formation of energy bands. And the range of energy of outermost shell, we call it a valence band, then conduction band. And the gap between valence band and conduction band is what we call energy gap or band gap. And this band gap gives idea about the electrical nature of the material, whether it is conductor, semiconductor, or insulator, etc. And this photo detection is an extension of semiconductor physics, which exploits photoelectric response exhibited by reverse bias PN junction or diodes. Normally, external reverse bias applied across a PN junction will develop a potential barrier across the junction, and it prevents the flow of charge carriers through the junction. Suppose the PN junction is exposed to light, and if the light is strong enough, it will be absorbed by the material, and the electron will be excited from valence band to the conduction band. Normally, this may be again recombined. So, but we want to make these excited electrons available in the external circuit. So this depends on the depletion barrier height. So these excited electrons will be collected in the external circuit. And there will be a proportionate increase in the electric current in the external circuit and the amount of current in the external circuit, which can be directly correlated to the incident light, or maybe intensity of light, or energy of light, or wavelength of frequency. And that is what we call photo detection. It's a very hot research topic, and across the globe, many research institutes, this photo detection work is going on. Actually, the quality of photo detection depends on various parameters like band gap of the semiconductor material, probability of absorption of the light by the material. These are the major parameters, so absorption coefficient, etc. Traditionally, 3D bulk material systems like gallium nitride, silicon, germanium, indium gallium arsenide, etc. have been used for the detection of wide spectrum of electromagnetic radiations. Even though the process is well established, it experiences various challenges in improving the precision and the quality of detection detection required, particularly due to low absorption coefficient or poor carrier mobility. Then there comes defective interface. When two layers are coming, there will be interface and there may be some defects. All these play a greater role in the quality of detection. Also, cost is another concern in 3D bulk systems. So the recent researchers on 2D layered materials have exhibited promising results in photo detection technology. So in our research, we developed thin film layers and heterostructures of 2D layered materials like molybdenum disulfide, MOS2, or MOS2 on aluminum nitride buffered silicon wafers, or MOS2 on various other semiconducting thin films, etc., to study the photo response over a wide range of spectrum. We generally, what we do is we grow 2 layers of thin films on commercially procured silicon substrate or aluminum nitride buffered silicon substrate. Then thin films will be grown using different thin film technology. We have got sputtering unit, then a pulse laser deposition to realize PN junction heterostructures. So here, so this is the pulse laser deposition unit which we are using in our the lab, that is Material Research Center, IISc Bangalore. And that right side, what you see is a laser unit. That laser, it is KRF excimer laser. And it's a very expensive laser and very rarely seen in many of the labs in Kerala, I suppose. And I did my PhD also in the same kind of this pulse laser deposition. And this is, when we are running that laser, I think it's, we need some gas. And that one cylinder, its cost is around 6 lakhs rupees or so. So it's very expensive. And IISc is having, I did my PhD IIT, and IIT Madras is also having the same system. And the left side is the pulse laser deposition unit. It is having a big evacuated chamber. A chamber is there, and the laser from that black section setup, KRF excimer laser, that will be focused. And that will go inside the chamber, and we can ablate. And generally, the people use this ND arc laser. It is comparatively less expensive, but this one, it is reasonably expensive. That is why it's not normally seen. I think even in, I don't know whether it is available even in Cochin University. I once contacted Cochin University also to do this experiment, and then they have got only ND arc laser, I think. Yeah. So this is pulse laser deposition. So here is a chamber, and in that chamber there is we can control the pressure using a pump. We can reduce the pressure inside. We can evacuate to a very low pressure of around 10 to the power minus 6 millibar. Then laser, which is a clean energy, which is coming from outside through a narrow window opening, and that will highly focused and high energy laser, which will reach the target. We call it target, something like our paracetamol like targets will be there of the material. And when it hits this target, extremely high temperature will be produced there, and that will cause, that is plasma, a plume will be produced. That material will be suddenly evaporated, and a plasma plume, ions of this material will be released. And that is what is shown in that color. And that will be directed towards a substrate, which is placed on the substrate holder just perpendicular to that. So when this plasma plume is reaching the substrate, this exactly the stoichiometry of the material will be maintained, and the same material will be deposited. But in many systems, sometimes the stoichiometric transfer may not be possible. Originally, this pulse laser deposition was very popular, particularly in superconducting systems like yttrium barium copper oxide, YBCO. That is having many elements inside, components, yttrium barium copper oxide. My this PhD work was on PMNPT, a material system, lead, magnesium, niobate, lead, titanate. So there is lead, magnesium, niobium, titanium, oxygen. So many are there. So when such a material is to be transmitted to get this perfect stoichiometry, normally many material, this thin film processing technique may not support. So that's why this pulse laser deposition came in. So and here the advantages inside we can model it. Actually, it is quite a tedious process compared to many other thin film technique because many parameters are involved. This distance between substrate and target, the pressure inside, then the energy of laser, then the kind of gas available inside, what is the pressure of that gas, how much time we are depositing, Then after deposition, how much time we anneal. That is, during deposition, we heat the substrate, so that when substrate is at a higher temperature, these incoming particles that can move on the substrate and finally get deposited in a proper way, and the exactly same material will be transferred. So we will get a perfect thin film. But only thing is, in PLD generally a very small, hardly 1 centimeters by 1 centimeter, that type of thin films are generally deposited. But there are some rastering mechanism techniques are also being used. The PLD system which I was using in IIT Madras, we had a rastering mechanism, so that when this laser will be moving left and right, and so that you will be able to deposit over a comparatively wider area. So that kind of systems are also available, but normally available PLDs, it is generally designed for a small deposition. So only thing is that we have to optimize. Many parameters are involved, and all these things have to be optimized, and then we will be getting very good quality thin film that can be used for a variety of many applications. This is the sputtering unit which we are using in IISc Bangalore. So this sputtering unit, again, this left side, there is a big chamber inside which we load the substrate, and inside this also will be evacuated before deposition, and we have the provision to heat it, and then there will be argon gas will be provided, made available inside, and a very high electric field will be produced. When high electric field is produced, argon will be ionized, and these ions will be moving at very high velocity because of strong electric field. And these moving ions that will hit the target, and species will be released. That species that may be directed towards the substrate, and it will be getting deposited. So both in sputtering as well as in PLD, we can load many targets, maybe 3 targets. 5 in PLD we can go even up to 5 targets. And in PLD we can control the number of laser shots. It is the number of laser shots which decide what is the thickness of this film developed. So we can, even by controlling optimizing the number of shots and energy, etc., we can get even 1 atomic layer thick film, thin film. Similarly, suppose you want to deposit 1 layer, maybe 1 or 2 atomic layer of one particular film, and immediately after that you want to deposit another atomic layer or another thin film, nano layer, then another layer, like that you can go for a multi-layer film. So here sputtering, in this system we have 3 main targets are normally attached. One is zinc, copper, and tin. So we can deposit zinc, or we can deposit copper, we can deposit tin, then we can go for these solar cells, Cs or Ts, copper, zinc, tin, and we can take it out and sulfurize. So this is the kind of device which we are working on, and its control unit is given on the right hand side. So we can give the required electric field, pressure, power, etc. So this is actually what is happening inside the sputtering system. So when these ions are moving at a very high speed, it will hit and it will knock out this species, and those that will be moving towards the substrate, and they will get deposited. So here normally large area deposition is possible. We can place so many targets. The big substrate holder will be there, so we can place many targets. So in our this research, we use generally this aluminum nitride buffered silicon, or pure silicon or platinized silicon. So these kinds of substrates we'll be using, and we go for these heterostructures. Maybe 1 layer we will give some maybe tin oxide, or tin selenide, or tin sulfide, zinc oxide, or copper oxide, like that. Then we may go for next layer MOS2, and we go for photo detection. So that's the kind of work I just started, and I spent some 30 to 40 days during this lockdown period last month, and we did a reasonably good work for that period. And now I'll be again going in the next month, and they'll continue. And I'm supposed to be there for 90 days a year, and the program is for 3 years. At least 90 days, I have the freedom to be there at time, and I can work. So it's really a blessing to be in IISc. It's a wonderful, beautiful institute, and a lot of facilities we can explore. So this is a kind of this top, what I am showing, that uppermost, that small 3 region sections are shown. That is a thin film which we have developed after sputtering. So tin is coated on silicon substrate. After that, tin we will what is oxidize, or we will sulfurize tin sulfide or copper zinc oxide. For that, we will use this tubular furnace. So that for the uppermost right corner, that photograph is nothing but it is the inside of that tubular furnace. So we insert the substrate after depositing the thin metal, then we'll push into the that chamber and heat it. If you want to oxidize directly, otherwise we'll allow some suitable gas to pass through, and they will get the concern, that is tin sulfide or zinc oxide or tin selenide or copper sulfide, something like that we can make it. And the left-hand side, what is seen is the photo detection, that instrument. This is the one which I used, and we got some good results as well. So this is one of the results I have shown here, that this is a photo detection, that is this directly the data taken from the device. After this, we'll put it in origin and make it in a better form in a presentable form. So in this case, see, this first one is 300 nanometer light was allowed to fall on this photo detector, and we got the detection. Then 400 nanometer. When it comes to 500 nanometer, it goes ultra, that is reverse. Then 500, 600, 700, 800, 900, something like that. Again, there is a shifting. That is what we call it photo switching. This is a very rarely seen in publications. So this is a good result. So we are trying to analyze and work on this going for further work on this. So these are two thin films are shown at the bottom. They are the photo detectors which we have developed. First one, we applied, or using this sputtering, we gave some tin oxide, copper oxide, etc. And then gave MOS2 through PLD. After that, some gold or silver deposition will be given through thermal evaporation. So that is what the complete device. Then that device will be placed in the that photo detection unit, and from that I have taken one photograph. That is what is shown at the bottommost, those gold dots. The same film, when it is in microscope, this is a kind of appearance. And the bottommost right corner, there is my photograph is also visible, and that is the instrument which is called molecular beam epitaxy. It's a very, very expensive instrument, and I think only very few, 4 or 5 are there in India, and I think it is not available in Kerala. And in IIT Madras, there is one, IIC Bangalore, there is one, and only few institutes in India having this device, and it's very, very expensive, and it is good if you can work on this. And I also have I own this device. Probably in 3 years' time, some point, I'll also plan some experiment, and hope I'll be able to do some research on this molecular beam epitaxy as well. So here a little bit of acknowledgement. See, many of these figures I have taken from Google Images. Then about Spark, I have already mentioned, Department of Physics Research College, I am also coordinator. Then these students, these are 2 research scholars in IIC Bangalore Material Research Center. Mr. Divendra Kumar Singh, he is working under Professor Kribanati and Professor Karunakarananda. And similarly, Mr. Kishan Kumawat, both of them are associating with my research. And Mr. Divendra Kumar is just submitting his PhD thesis this week or so. And my project is with one faculty in this other centrally funded institute. So my proposal was supported by Professor Karunakarananda, Chairman Material Research Center IIC Bangalore, and I'm getting all support from him to do this photo detection and material research. And we are funded by CRB Government of India through project number KR 2020-241. So this is the work. And this is my college, Sacred Heart College, you must be familiar with. And the right side is Indian Institute of Science, Bangalore. So please look for such institutes, IIC Bangalore, IIT Madras, or IITs, or ISOs, NITs, so such great institutes. Please try. That is a wonderful place where you can explore, and you will enjoy science. You will feel that whatever the science you learned, you can experience, and you can see how students are working. And there are a lot of opportunities. After that, you can even try for Germany, US, etc., such places where PhD, postdoc, etc. are available. And if you complete this and come back, there are many opportunities waiting for you. So many research institutes in India now. Centrally funded institutes, CSIR labs, IITs, ISOs, IAC, all these institutes, they are looking for a very smart dynamics, these researchers. So please have a great big aim when you are celebrating this Science Day, and try to I'm sure this is very close. You have reached a point very close to that hitting the target. So therefore, this is a point where the number of people who are having the confidence to try is less. So many leave after BSc. They feel that, oh no, I'll go for bank coaching. After MSc, they'll say that no, I am interested in something else. So please stick on. If you are having some passion in science, please stick on and be confident. It's not money that matters. So researchers may not be making that much of money compared to many of these software companies, but this will bring you some satisfaction which nothing else can give. So you will be experiencing a different kind of pleasure, and that is the beauty of science. So I invite all of you to think seriously, sincerely, and plan. If you have some passion in science, please make it beautiful. Because we all are young scientists. We have something in our mind. So that is why you came to physics, and being a physics student is really amazing. Okay, so please do something. So again, see, I have shared my site that piustin@sscollege.ac.in. If you go there, I used to do a lot of these talks on X-ray diffraction, superconductors, and other these BSc, MSc classes. All these are available the links are available there. Also, I have prepared a lot collection of PPTs, which are useful for school and BSc, MSc students, particularly useful for your JAM net coaching. So please access those also, and I have given the name Love of Science and Humanity. There's a terminology used in that particular link. So if you click that, you will go to the Google Drive. From there, you can access all those things. So these are something which I thought of sharing on this beautiful day, National Science Day, and it was really amazing. I was very happy to accept this invitation when Madam Vimala contacted me. I was really happy because I know that I have heard a lot about St. Xavier's College. And I had a few friends when I was doing my MSc also from St. Xavier's College. So it was really amazing interacting with those students also, I still remember. So anyway, thank you very much for inviting me, and it was really a nice experience. Thank you.
Thank you, sir, for the great session and your words of motivation. Now, we have come to the end of the session. If any of the participants have any doubt, you can post your questions in the query. So you can check if there is any questions. Otherwise, we can move on to the next session. Students can post their questions, or you can unmute and ask sir directly. Okay, then we can move on to the next session. Now we have come to the end of the session. I would like to thank our esteemed speaker, Dr. Pius Augustine, for giving us his valuable time and presenting us with such a wonderful session. Today's webinar gave us great insights into the topic, and I'm pretty sure the precious knowledge that he has given us will definitely help everyone present here in their studies and future. Once again, I would like to thank Dr. Pius Augustine for taking out his time from his busy schedule and enlightening us with knowledge. Thank you so much, sir.
Thank you.
On this occasion, I would also like to show our gratitude to the Academy of Physics Teachers, APT, and DBT Star College Scheme for providing the financial support to celebrate the National Science Day with a variety of events for the students. I would also like to thank our beloved HOD, Dr. Sheena Xavier, for her guidance and sharing with us her enthusiasm to conduct such great sessions for the students and faculty alike. I also want to thank our dear teachers who worked hard to make this event successful. Also, thank you to all the participants present here for paying your attention and learning. I would end my speech here. Thank you. The link